We are recording. So you're going to show us a Rust? Okay.
Yeah, I don't think I've ever had to share my screen before. I'm trying to figure out how to do that.
Cursor to the middle of the bottom of your Zoom window. Our screen.
The big green button. There we go.
Select the desktop you want to share, and then hit the share button.
Okay.
No. You see your screen.
All right. So, yeah, I recloned it last night. It's been about 3 months since I worked on this. Let's see. Where was it?
I don't know if you can increase your font size a little bit.
Oh, sure. You want it bigger? How's this?
Awesome.
Does that look okay? Okay. So, yeah, as I said, it's been a minute since I've worked through this code, but it's supposed to be a full spec of a Hashgraph. So basically, it's all the functions that you need to determine finality for a specific event. And so events have like a similar concept that you can kind of see in most consensus algorithms, like the one that we've been working with recently with parity, which is the ghost and grandpa, and it has this concept of kind of a pre-vote and a pre-commit, which the pre-commit is where you reach finality. So a pre-vote, you're basically looking to get like 2/3 of people in the validator set to see your event, and then once 2/3 have seen it, you can say that that event has been seen. And then once 2/3 of events that have been seen have seen your event, then you can say that your event has been strongly seen, and that's kind of like reaching finality. Once 2/3 of events have seen your event, 2/3 events that have been seen have seen your event, then your event can no longer be changed or anything like that in the future. Does that make sense?
I think so. Did you say, was there two steps or one step? It's you get 2/3 of the vote, it's final, period, right?
Yeah, there's not really voting in Hashgraph in like a conventional sense. It's more just kind of what you see based on,
right.
Yeah, which nodes communicate with which other nodes. So events are usually sent to another person. So I guess I should step back a little bit. In Hashgraph, they say that you're gossiping about gossiping, and the idea is that you take an event, and an event may or may not contain any number of transactions, so 0 or more. So you can just send an event that says, I saw an event from somebody else and I'm letting somebody else know. And that kind of just perpetuates the hash graph. And so the events themselves are the gossip, and in some ways they're the votes, but they also can contain transactions. So it's kind of this like weird recursion.
It's what I term virtual vote.
Yeah, virtual.
I would make this vote.
Yeah, that's a good way to look at it.
I've seen this, so I would agree with it, whatever.
So here I just defined in an enum what an event can be. So there's either the genesis event, which only has a creator and it has no parents, and no transactions, or it's an update event in which each event has a self parent and an other parent. So this part is a lot more clear if you look at the paper. They have some pretty diagrams.
Just real quick, what do you mean by enum? What is that?
Enum, it's like a sum type.
Some type. Okay.
It's an enumeration.
Yeah. Okay.
Yeah, enumerator. Did you ever work with C++ or anything like that?
Not directly. No.
Hmm.
By some type you mean it's like a one-off type, or is that something different?
Yeah, it's like an either or. It's like a
Yeah.
choice.
Okay. Yeah. Okay. Cool.
Yeah. So yeah, you can see in this diagram here, this is just an example of a hash graph. These bottom nodes are the genesis nodes, and then it moves up through time. They do have some concept of time, but there's no like global synchronous clock, kind of like we were trying to deal with in Grandpa. But yeah, so you can see that every node is going to be connected to, or every event, which is a node, is going to be connected to its previous event by the same creator. So one line is a creator, and an event usually occurs when a creator receives an event from another person. So that's why this line from this creator to this creator is on this event. And then it's also possible for an event not to just be created out of thin air for whatever reason. Maybe this guy hasn't seen an event in a really long time, and so he kind of just passes on some information, whatever that is. So if we look back at the code, we have the self parent always, and the other parent is optional. And then vector of transactions, so that's the 0 or more. So an awesome thing about Rust is that it's really easy to derive traits. I mean, you get this in Haskell too or anything like that. But so up here we're deriving serialize and deserialize. That's from the, I don't know how to pronounce this, but it's like this Serde library. So an enum type is really easy to serialize, and then these are all strings, and transaction type, which I define somewhere else. It's a really simple type right now. So this can super easily just be serialized to JSON, which makes it really easy to work with. For one, to hash it, if we want to hash it, then can just give serialization of the JSON. That's what I do here.
Oh, cool.
Yeah. So let's look at the code.
So because it's an enum, wouldn't that mean that it's a one of and it couldn't have more than one of those values?
Say that again.
Okay, the event is an enum, right?
Right.
So, okay, so it's either an update or a Genesis creator. Is that what you're saying there?
Yeah. It can either be an update or a Genesis. So Genesis is obviously always the first one.
Yeah, I was thinking it could be a creator or a self-parent, or that's a structure. That's not part of the enum.
Yeah, right. Yeah, it's one or the other.
Okay, thanks. Sorry.
No problem. Okay. So graph. Okay. So this is the code where we have all the functions to determine like if an event is a witness, if an event has been strongly seen, and also Hashgraph has a concept of rounds pretty similar to Grandpa. I'm pretty sure they're super similar. We'll find out. Again, as I said, it's been a while. And so I wrote a test down here to kind of like show through how this works. So we can start from here. this picture right here is what the hash graph we're building is going to look like. So here's the genesis down here, G1, G2, G3, and then we have some events passing back and forth. And so we have a really ugly creation of it. This is all the creation. These events. Let's see. Let's start with what some of the tests are. So we test for ancestor events. That one should be pretty easy. You're basically just going to traverse through the graph. And let's look at the top structure. So this is the actual graph structure. This structure right here. So, you know, one of the interesting things about Rust is that it has linear types. So you can't point to the same object more than once. So, you know, that can be tough for any kind of graph or even a DAG sometimes. But luckily in this case, all I'm doing is I'm just storing a hash map of string to event values. And, you know, some people would consider that dangerous because if an event is removed in the future, then, you know, that this string is basically like a null pointer. But if you go look in the Hashgraph paper, they basically say that in the event of like malicious behavior or something like that, the event is not destroyed. It's just basically archived. So there's no actual deletion of events in Hashgraph. So this is actually just fine.
Cool.
Let's see. Your ID, I don't remember what that is. Let's see. We have the creators, it's the validator set. And then I think these other things are kind of just like some caching mechanisms I use, because when you're, you know, iterating through graphs recursively, you usually want to do some kind of dynamic programming.
Mm-hmm.
So let's see. The other interesting thing that I did on the events is made an iterator. I think the iterator, let's see. Yeah, so it's like it's a separate structure that has a list of nodes, and it basically allows you to iterate from an event backwards to its, I guess it's self-parents and also other parents. Let's see. So yeah, the iterator basically just runs through so it pushes the self-parent, and then on the next, it'll grab the other parent. That's what it is, yeah. So, yeah. Rust has traits, which are a lot like,
Like
what
a
would that be
Scala
like?
trait.
Yeah, like traits.
Well, like traits in Scala.
Yeah, like traits in Scala, that's right.
Okay. Okay.
Yeah. Yeah, exactly. So the iterator just has a next function, and I think what it's doing here is that it's basically just exhausting the list of other parents that it runs through, and then it also iteratively puts the next self-parent on and then runs through that other parent list. So you're basically running through the entire graph of everything that edge or that event is connected to. So like this guy right here, if you iterated through him, would go through all the other parents. So it'd go to this guy, this guy, this guy, and then it'd recurse back up, go down to the self-parent, run through it again. Like that.
Does anyone remember what traits are called in Ruby? It's in my memory somewhere, but I lost
No,
it.
honestly, I didn't know.
I don't know
Ruby.
any Ruby.
Yeah, I didn't know Ruby had that nice of a feature.
Yeah, well, I mean, it's basically, in small talk, we just called it includes. We wanted to include some protocol in a class.
Mm-hmm.
Okay, which, you know, is some, I abstract operations that are part of the language of the object that we want to support. And because of essentially polymorphism, you could, as long as the class supported the methods that were used, the includes would work. In Ruby, the whatever would work, or in Scala, the traits, unless I have the idea of traits wrong. But that's my understanding of traits in Scala.
Yeah, that sounds like it. But Ruby's also a dynamically typed language, so it seems like maybe you could add on or include features to it, but you couldn't necessarily like use that like typing system, the trait generic types in functions, or like write higher typed functions. But I mean, yeah, I don't know. I don't know Ruby very well. Okay, yeah. So yeah, the point of this iterator is just that it iterates through all the events that can see that object. That's the point of it. So it makes it really easy to write functions for like, everything we're trying to determine, because it doesn't iterate through any events that wouldn't see that event. Okay. So the easiest one is ancestor, which basically just takes the reference to the event and sees if another event is its ancestor, gets the two events, and then it iterates through the first one and checks each event to see if it's the second one. It's pretty simple. So let's see, strongly see. Yeah, I'm trying to remember all the definitions, but I guess, okay, let's run through strongly see and see exactly what the criteria is. So, okay. So we've got creator scene, sort of filtering for ancestors of X, and then, okay, so here we're just getting any unique creator. We're building a creator list for whatever reason. Oh yeah, so not the entire validator set, only creators seen. And then, oh, interesting. Yeah, that's right. So yeah, to strongly see, it has to be 2/3 validators. So we're going to see if this set of creators seen is greater than 2 times n divided by 3, where n is
the entire validator set.
Yeah, there you go.
Nice.
Yeah. And add self to scene set in case it wasn't jurist. Oh, right. Okay, yeah. So this is just a safe checking. Yeah, so that's pretty easy. Yeah, I really liked this because the iterator makes it really easy to like write all these functions, even if it's not super efficient. Makes it easy to conceptualize.
Yeah, that's kind of how I'm working in K right now. I'm just doing things in an intuitive way, or what I feel like is an intuitive way. And once I get something working, then I'll go back and worry about optimization and all of that stuff. I just want to see that things work first, before spending all that effort to optimize while developing the code. I think is maybe not the best way to go.
Yeah, you're going to get lost in a rabbit hole that you'll never get out of.
Right, yeah, and you're just trying to optimize something, and it's like, you kind of lose the forest for the trees a little bit.
Absolutely, yeah. I still run into that issue like every day, even though I know not to.
It's the agile difference. Incremental prototyping. One step at a time.
Yeah, right.
You don't try to solve the world.
Yeah, you don't I don't know, you don't compose an essay in one sitting, right? Or, oh, well, I don't know. That's the lesson that I constantly learn every time I try to write an essay, because I always try to write it in one sitting, but it's not the way. It's not the way to do it. I can tell you that from experience.
Yeah, I feel like that's the dream of people that, trying to learn Haskell and all this stuff is we want to write the most beautiful, perfect, elegant code in, a really short amount of time.
Mm-hmm.
But, I don't know if it actually works that way. So, okay. All right. So we have a concept of being famous for an event. An event is famous if 2/3 future witnesses strongly see it. Okay. Yeah. That's where things get interesting. So strongly see is about the past events, two-thirds creators in the past. And being famous means that, you can't determine if an event is famous as soon as it happens. You have to wait for 2/3 of future witnesses, which we haven't defined what a witness is yet. So let's go do that first.
Yeah, I was going to ask what a future witness is, but maybe we should talk about what a witness is first.
Yeah, and hopefully we can figure it out from the code, because I can't tell you off the top of my head.
Oh, yeah, cool.
I mean, it makes sense that, it's one thing to see that 2/3 of the validators have seen it.
Mm-hmm.
And it's another thing to see that 2/3 of the validators also see 2/3 of the validators have seen it.
Yeah.
So that's famous, but it's already been finalized, right? Even if it's not famous.
Oh, that's famous when 2/3 of the validators see that 2/3 of the or see that each one of the validators they see sees 2/3 of the validators have seen the message or something along those lines.
Yeah, 2/3 future witnesses strongly see it. For a witness, I don't know. Let's look at the code, because I don't want to.
Yeah. All right.
Well, if they strongly see it, then they see 2/3, right? If 2/3 strongly see it, then 2/3.
Mm-hmm. Mm-hmm.
Yeah, but it's not just that the other validators, 2/3 other validators see it like with any event. There's some special criteria for the event itself that makes it a witness. I think it's like an event that's the first event in a round by that creator or something. So maybe the idea here is that you have to iterate to the next round before you can determine if an event is famous. Maybe.
Oh yeah.
So
Now,
okay.
Do you start a round when you finalize the block?
It's more complicated than that, right? Because I remember you saying you could start a round almost at any point in time.
Yeah. I can't remember exactly what it takes to start a round. And I think I have a function for that, determine round. The round an event belongs to, which is the max of its parents' rounds plus 1 if it's a witness. Okay, so yeah, so we got to figure out the definition of a witness, and then everything works off each other. Yeah. Okay. So we determine if some event is a witness by, if it's the genesis, it's a witness, and if it's an update, then okay.
Wait a second. An event is a witness?
Yeah. So it's not the actual validator itself.
Okay. Huh.
Yeah.
So Genesis automatically is a witness.
And then, okay. So if the round of the event is greater than the round of its self-parent, then it's a witness.
Okay, strictly greater than the round of the self-parent. Wait, can you remind me what this update self-parent thing is about that you're pattern matching against?
Oh, yeah. which part do you mean? Do you mean like the syntax, like this right here?
Because you have the two things, right? It can be Genesis or it can be update. And we're just saying that update has that first, characteristic or whatever that is self-parent. And then you're just using
exactly.
that in okay. You're just measuring the round of that self-parent. Okay, that makes sense.
Yeah. And the dot is just a way to say that we're pattern matching on the struct update, and it has some other stuff we don't care about.
Cool. Yeah, it's like a wildcard or something, I guess.
Yeah. Okay, so a round is determined by the witness, and a witness is determined by the round. So this is getting weird. Let's get round out function.
Some mutual recursion going on here.
Okay, so
it's like your witness, if it's potentially a next block for you, because it fits right on top of yourself? No, never mind.
So it says here that the round of an event for Genesis, it's R, which I'm pretty sure we haven't looked at, but I think I defined Genesis of R to be just round 1 or 0, just one of those. And then the other one is going to be, we're going to iterate through, I think round index is all events. It's just a set of all events in this round. As I mentioned, in the graph, there's those caching structures. So we iterate through all those events, and we find an event that contains the round the event.
So who knows this round index? Like, is this information? So it's information that each of the creators or validators have access to, right? Or they all are recording it individually?
Yeah. So that's a good question. Let's look at round index. It's a vector, hash set, strings.
There it is. Oh, well, not being defined.
Set events round. So yeah, an event. So when you create a new event, it's pushed onto the round index. Yeah, that's interesting. So
yeah, is it?
It is kind of a global concept, right?
Yeah. Okay. So this round index notion is some information that everyone is gossiping to one another, right? So I guess you can assume it's just a value that's come to consensus on or something.
Yeah, it's not actually an idea that's constructed in the paper. It's just something that I use here for like efficiency.
Yeah, right, for the caching stuff.
Yeah. Interesting. I wonder if I defined a separate iteration of a round index. Yeah. Wow.
Can you just say really simply what a round index is again? So it's I don't even know how to ask what I think it is.
Yeah. So that's a good idea. This is the add event function. Yeah. So you're just adding event to the graph, and so you determine the round of an event, and then if it's whatever the current round is, if the new event that you're adding is the same as the current round, then you add it to the current round index. Yeah. And if it starts a new round, then you push a new round index. So it really is kind of like somewhat of a global concept of round index.
Okay, so it's so the round index for some particular round number just has all of the events in that particular round.
Yeah, exactly.
Okay, cool.
Yeah. So yeah, that's a good question. I feel like there's definitely potential there for that to not match the paper, because I would have to go through and look at this again and see what I was thinking.
Yeah.
But yeah, it's definitely possible that like two events might not be able to see each other in a round, and therefore not be able to determine totally this. I mean, you could pretty simply like, so this code can run on a specific node just the same, and they can still build their own round index. And when they receive events from other nodes, they can build that up. So each node or each validator can have its own concept of a round index, and it might not be the same as everyone else's.
Yeah.
But I think that's fine, because you're still just computing what you think to be true about the event. So like if you can strongly see, or if you believe that an event can be strongly seen from your perspective.
Yeah, and it sounds like if there's some strongly seen business going on, then you might get a 2/3 consensus on the round index anyways, and that's probably enough. But I'm not really sure.
Yeah. So there's not really like a consensus idea around round index, but there is a consensus idea around an event being famous or something like that. So I guess in that respect, that a round index is at least sufficiently true once you achieve if an event is famous. Yeah. So I think the concept does work. Here, you're kind of like using an ideal scenario, but it would work even with partial information. What were we looking at? We were looking at determine witness. Yeah. So, okay, the roundup is kind of confusing to me. Why don't we look at determine round? Because that's kind of like what we need. Like the most obvious case would be like, how do you determine? So if an event is in the genesis round, then it should be round 1, right? So somewhere insert, they might not even get their own round, or there might be a determined and determined round. So if an event is genesis, it's round 0. There it is.
Yeah.
Okay. If it's an update, then okay, so here is just if we're calling it twice, then cast the result and only evaluate once. So if R has been defined, then return it. Otherwise, its round is the max of its two parents, its self-parent and its other parent, if it has another parent. Otherwise, it's just the round of its self-parent. But this isn't totally true. I think this is just ER, so we're just getting the max of the self-parent rounds. And then next we need to iterate through all the events in this current round except for itself. And what do we do with it? Find out how many witnesses by unique members the event can strongly see. Okay. Yeah, so we looked at the definition of strongly see, right? The 2/3 of the set of validators can see it.
Yeah.
So that's all this means. So we're getting For each round, find out how many witnesses by unique members the event can strongly see. So I think the idea here is that, yeah, okay, it says it down here. If an event can strongly see 2/3 of the of events by other validators, then it can step to the next round from where it is. So that's
okay. So they're actually increasing the round number here, if that's true.
Yeah, exactly.
Okay.
So an event is the max of its two parents plus 1 if it can see more than 2/3 of events from other validators. Or strongly see. Yeah. Strongly see events from 2/3 of other validators. Okay, so I think that makes sense. I'm wondering if they have an example of it in the paper that we could look at.
Yeah, that would be great.
Yeah. Okay, I think they do down here.
Yeah, just I feel like I'm having the same issue with Hashgraph as I am with Grandpa, and it's just like there's so much like terminology that's introduced that I kind of forget what the concepts are as we go further on into it, and then I'm like, wait a second, what was this other thing, and what was famous, and what was strongly see, and yeah, it's a lot to keep track of.
Yeah, these algorithms are just, they have so many definitions that like build off each other completely.
Yeah.
They're like, yeah, it's tough. I don't know.
Okay, cool. So here's an example.
Yeah, so let me just read it. It says, illustration of strongly seeing. In each hash graph, the yellow event at the top can strongly see one of the orange events on the bottom row. There are n equals 5 members, so the least integer greater than 2n/3 is 4. In D, one event orange is an ancestor of each of 4 intermediate events by different creators, which are red, each of which is an ancestor of the yellow event. Okay. So therefore, the yellow event can strongly see the orange event. So, okay, yeah.
Oh wait, that's specifically in the D example?
Yeah. So it's saying that yellow can strongly see orange because orange is an ancestor of 4 intermediate events by different creators, which are in red. So you can see that the yellow, yeah.
Okay, by different creators is the important part, right?
Yeah. Okay, so an event.
Yeah, by 4. Right. Okay, that makes sense to get that 2/3 majority or whatever.
Cool. Yeah. So yeah, it's kind of weird here. I'm trying to remember how it is in Grandpa, but like the concept of strongly seeing. In this, it's like it's not a validator strongly sees an event. It's that an event strongly sees an event. Remember if that's similar or not. But yeah. So yeah, that's a pretty simple concept. So okay, each of these, the other concept. Let me just keep reading because this also goes on, I think, to determine how you can say that yellow is in the next round.
Cool. Okay.
So therefore, each of the other hash graphs is colored to show the same for a different orange event on the bottom row, which the yellow event see through at least 4 red events. If all 4 orange events in both parents of the yellow event have a created round of R, then yellow is created in round R plus 1 because it can strongly see more than 2n/3 witnesses created by different members in round R. Note that every event is defined to be both an ancestor and self-ancestor of itself. Okay. So yeah, remember that it's 4 is the 2/3 point. So
Yeah.
so one of these graphs can strongly seeing another event, but because yellow strongly sees 4 different unique events by unique validators, then this entire construction right here is a proof that it can move on to the next round, R+1.
Okay. Okay, so so which dot is the witness in this round, or which event is the witness? Is that the orange ones?
Yeah, that's a good point. So yeah, remember Genesis just by definition is a witness.
Yeah.
So that's why we get that here. All the Genesis
Okay.
events are witnesses. And
Oh, yeah, I was thinking like, yeah, I guess that has to be Genesis, right? But I was thinking they just cut the graph at some point, and we're just looking at bits of it.
yeah, no, I
But
think it does have to be Genesis.
yeah, okay. So they're saying that yellow. I didn't even realize that we were looking at the same graph in all 4 of these pictures. I just saw the colors were different and wasn't really paying attention to it. But okay, so these are all 4 graphs that are the same exact scenario, and so they're saying yellow can see 4 different witnesses, right? And so it sees the 2n/3 majority of witnesses created in some particular round, which we're calling R. So then yellow knows it's time to start round R+1.
Exactly, yeah.
Okay, cool.
Yeah. And then the other thing here, I'm pretty sure, I'm just going off of memory, but I'm pretty sure that each validator's first event in a new round makes it a witness.
Mm-hmm.
So yeah, yellow would be a witness event in this case.
Okay, so yellow is automatically a witness of round R+1.
R+1, yeah.
Yeah, cool. Okay, that is kind of making some sense. This example helped a lot for me.
Yeah, me too. The colors really help.
Yeah.
Yeah, so that gets the idea of strongly seeing and then of a witness in a new round. So really only the last concept is famous. I'm just going to collapse that. So yeah, and that does make sense. Let's look at this one more time just for my own sanity to make sure. So we get the number of witnesses that are strongly seen by iterating through all the events in this round, seeing if they can strongly see the event.
Mm-hmm.
Oh, okay, if the event can strongly see them, yeah. Yeah, so we're building up this set, and okay, and yeah, because it's a set, we're inserting the creators, and so therefore you never have to, it's only unique creators. So that's how we determine if 2/3 in or 2 times in.
Oh, yeah, sure, right. Because if that creator was already added, it's a set. It just doesn't add anything to it.
Yeah, exactly.
That makes sense. Okay, cool.
Cool. All right. So determine witness. That makes sense now. That's an easy definition. If the event is greater than the round of its self-parent, then so yeah, that's like what I said. An event is a witness if it's the first event by a specific validator, which is why it's only checking the self-parent.
Mm-hmm.
It's the first event of a new round by that validator.
Yeah.
So determine if the event is famous. An event is famous if 2/3 future witnesses strongly see it. Okay, so this one is a little more complex. Can you kind of imagine what that would look like?
It's famous if 2/3 future witnesses strongly see it.
Think of how to like.
Yeah, so future witnesses are just events that happen after this event. And, all right, I mean, I'm assuming that's what future witnesses means.
Yeah, exactly. So it's interesting. This is the first criteria where instead of looking backwards, we're looking forwards, or we're working backwards from the future.
Right.
And we know that it at least has to be determined from round R plus 1 of whatever this event is in round R.
Oh, wait, it's almost like we have some mechanism or algorithm that's like propagating downwards through the rounds and determining if like new rounds should be created. But then this is famous things almost seems like it's propagating from Genesis up through the rounds and like, making famous determinations as it like traverses up the graph.
Yeah, but the tough part there is that, because it's kind of like a DAG, it's really hard to traverse upwards because and you might not even have the concept of like a doubly linked node. So usually I think what we do is we determine, actually I don't even remember, let's just go through it. But yeah, that's the idea is you're pointing upwards in some respect. So we're determining if a specific event is famous. If it's not a witness, return false. Okay, so an event has to be famous, or has to be a witness to be famous, I guess, is what this is saying.
Okay.
What else? So we get all the witnesses by self.events values. Okay, so this is interesting right here. We're iterating through all events that we know about. And we filter by only the famous events.
Okay.
And we strongly see, so we're building up a hash set of creators again that strongly see the event. Okay, yeah, so this is interesting. So yeah, if we look back up at the, this is the determine round function. We had similar looking code here for strongly see, but we're seeing if the event that we care about can strongly see 2/3 of other events that we're iterating through. So event hash and e.hash. Where e is just the iterated event. And then down here, we have the opposite, where we're seeing if the iterated event can strongly see the event that we care about.
Yeah, interesting.
So does Rust do lazy evaluation, or?
It can, but it isn't by default, and it's not what it's doing here. But yeah, that would definitely make a lot of things in this code a lot more efficient. Let's see. So, okay, the reason that I'm iterating through all events and then filtering by is famous is probably just because I didn't, want to make another caching mechanism for famous events, but I'm sure you could do that pretty easily. So that's just an example of it not being optimized. But so we're basically just iterating through all the famous events that we know about and seeing and building up a set of unique validators or creators of people that have famous events that can strongly see the event we care about. And then we say that if 2/3 of the validators have a famous event that can strongly see the event we care about, then the event we care about is famous.
Whoa, this is the definition for famous, right?
Yeah, it's weird because it's recursive, right?
Yeah, I was gonna say it's almost weird that it's so you said that we're checking if 2/3 of the validators have famous events that strongly see this particular event that we're checking for being famous, right?
Yeah, I think
Yeah,
so.
that's so weird. So it's like so we're looking into the future to see if validators strongly see this particular event, but we have to know their famous events to ask the question of whether their famous events strongly see this one, which we're trying to determine as famous. Something about that seems really weird to me.
Oh, yeah, you're totally right. Yeah, you're iterating through events that we already know are famous to determine if a past event is famous. Yeah, so I'm wondering like what the base case is here. Like Genesis events, are they famous?
Yeah, is a Genesis event famous?
Let's do a search for all places where. Okay. So, yeah, that's interesting, by the way. I don't know if you saw this comment, but some false means it's just a witness, but it's not famous.
Oh.
And witness. Okay, so here we're just saying which function is this? Add the event. Okay, yeah, so here we just say it's a witness, but not is famous. Here we're getting the fame. Here is famous. We're determining it.
Yeah.
Huh.
Oh, wait, there was something about Genesis in that thing is famous. Oh, yeah. Genesis event is famous by default, it looks like, or by definition.
Yeah. Oh, nice. Yeah. There's the basics.
Yeah. Okay.
Yeah. Okay. So, but a Genesis event is never going to strongly see another event.
Yeah, and the Genesis event isn't a future witness of anything.
Yeah. So, let me see this test down here. So we test to see. Okay, these are only the Genesis events. Yeah, I don't know if I ever reached or like tested for the concept of a future event being famous.
Yeah.
Or even built the graph out to reach that far.
Yeah. So do you have something that generates a graph so you can actually generate some examples of these things?
Yeah. So I mean, this right here is the part that's generating this graph. This is what
Okay.
Yeah.
Oh, so it actually outputs that graph.
Yeah, I mean, it doesn't really like have a visual. It basically just generates it and then runs a whole bunch of different tests over it. Like.
Okay. It's just like an abstract thing that it keeps.
Yeah.
Okay.
Yeah. And yeah, the idea is that this would be, just one local validator's like view of the entire graph.
Yeah.
And the add event function would be called either when he creates an event or when he receives an event from somebody else.
Yeah. you know, I don't know how much work would go into doing this, but it would be cool to have it actually generate like a dot file or something that you could look at the actual graph structure in.
What's a dot file?
So I know dot is the language that I'm not sure if I'm saying this right, but GraphViz, like whatever language you use for GraphViz, I think that's called dot. So you can, there's like some nice syntax for generating really cool looking graphs, and they remind me of graphs in LaTeX, but I never got that far into generating graphs for LaTeX.
Gotcha. I feel like I have seen GraphViz before.
Yeah, it's pretty cool.
I think when I looked at it, it seemed like it was a pretty old technology. Is it still?
I really don't know.
Hmm.
Yeah, I've only used it a very, very little bit, but just talking about these hash graphs kind of made me think of this again.
Yeah, definitely. That it would be very nice to have this kind of and see like new events being appended in real time and potentially like their colors changing.
Yeah, that would be super cool.
Yeah, yeah. There's also D3. Do you know that framework?
I don't know.
In JavaScript. It's basically like a data visualizer, but also really good for graphs.
Okay.
And rendered in a browser.
Oh, okay.
JavaScript.
D3. I'll have to check that out. Yeah, because I would love to generate some kind of different visualization for some of the stuff that I just don't know how to use, and I haven't looked into anything seriously enough to start.
Yeah,
but I'll look into that one.
Yeah, it's something I want to play with more too.
Yeah.
It's a lot more exciting than kind of just like running tests and.
Yeah, right. And not to mention, when you show other people, they'll be a hell of a lot more interested than like just showing them all this raw code, and you're just like, yeah, this is supposed to generate this thing, and
yeah, it's true. Yeah, it's crazy. You know, even as programmers, like visualization is so important to us.
It's huge, man. Like a lot of the time, like, I just think very geometrically, you know. So a lot of the times I have to draw pictures to be able to program something the way that I want it to be programmed, you know.
Yeah, totally.
Yeah, this is pretty cool stuff, though.
Yeah, I'll look more into that Is Famous event. Let you know if I figure anything out about it.
Yeah, cool.
One of my dysfunctions is I don't think visually or graphically at all.
Oh, really? I can't help it.
Yeah. It took me, you know, like 50 years to learn that I had to make diagrams in order for other people to understand what I was talking about.
Yeah, that is the best outcome, is that it's easier to explain to other people when you have a picture.
Yeah.
Mm-hmm.
Hey, Jay, I had a quick question. That code that you were showing, so is that a fork of original code, or did you create all of that yourself?
Yeah, that's all done by me.
Okay, cool. Are you part of the Hashgraph team or the organization in some way?
No, I'm actually not. And I actually contacted them about this, and they were very interested in it. I was a little concerned because the Hashgraph is a patented algorithm.
Okay.
Oh, yeah.
But they seemed quite all right with it. So.
Couldn't we plug this into Substrate as consensus mechanism?
That would probably be taking it too far. They would probably come after me.
Hey, but you developed it all on your own, right?
Yeah.
Yeah, that's what I was thinking of. Is like, hey, you know, Substrate Hashgraph, and what kind of possibilities?
Well, we would do it academically to compare performance of
right.
Substrate to Hashgraph.
Yeah, they might have a problem if you launch an ICO with that as your consensus algorithm on your blockchain.
Fastest consensus ever.
They have an actual patent?
Yeah, I'm pretty sure it's a patent, IP patent on the technology. I've actually met Lehman Baird, who's the creator of Hashgraph. He lives in Dallas. I met him a few times in events. Super smart dude. He also could use a picture.
So, and what is Hashgraph's future plans? Do they plan on developing a blockchain and have infrastructure and have some type of cost accounting associated with it, or is just academic? And do you know what?
No, I don't know exactly what their plans are. It might be similar to our chain. I don't think
Okay.
I think they're actually aiming for more like business to business applications and not to have one chain, but rather use the technology in different places.
Okay.
But I'm not sure. I mean, honestly, we could contact them and ask them what they think about us and, putting this into parity, like substrate. Or something like that.
Yeah, that's as Joshi, it progresses and educates us all, and we're all kind of connecting the dots to this new world of blockchain and other things. There's Hashgraph is going to provide, we don't know exactly how it's going to fit in, but just knowing that it's there creates this flexibility, this world of possibilities that didn't have, and that's what Substrate and Polkadot and all that kind of presents. So
Totally.
it creates this broader ecosystem of possibilities.
Yeah, and Hashgraph is like really exciting with the idea of gossip about gossip. Like, I didn't give it justice here, but the idea that you never have to vote on anything, virtual votes, and you never have to add any extra information in the graph. Like, I think there's some kind of proofs that this is potentially like one of the most efficient ways that you can reach a consensus, at least as far as the amount of different like separate communication events that you have to relay.
Yeah, I spent the time and watched an hour's worth of that gentleman's who you mentioned who created this, and that helped me get sort of a foundation of Hashgraph. And gossip on gossip, a lot of these concepts and ideas made a lot of sense. So it's all great stuff. What were you saying, Jim?
Yeah, I was not sure anymore, but that's my understanding was that Hashgraph was supported by fees that went to validator rewards. Their blockchain.
I didn't hear that. What'd you say?
My understanding is that Hashgraph supports fees for transactions that are applied to validator rewards.
Mm-hmm.
Okay, so if you validate a transaction, whatever, you get something.
Okay.
But now I'm not sure.
Yeah, because there's not really a concept of validators or validation in Hashgraph. It's more just each individual creator can determine if a block is, or if an event is valid or not.
Well, there still could be equivocation, right? You still have to validate.
Yeah, but you don't really like let anybody know or vote on equivocation or anything like that. It's more just that you can see equivocation or you can't. And if you can see it, then probably with enough time, everybody else can see it too. And if you can't, then you just wait because it means that you don't have a finality yet.
Jay, so with your code, do you plan on adding to it and continuing on in some capacity, or do you feel like that project has kind of reached its endpoint?
I mean, I might pick it back up. I wrote this 3 months ago, so it's been a while. But I left it in a clean place. Sometimes you write code and you feel like, oh God, I never want to look at that again.
Yeah.
But no, this isn't one of those projects. I feel pretty good about it, so I might pick it back up again. I was trying to to integrate libp2p in it so that I could see it working over a network.
Yeah, you know, if you explore the possibility of the GraphViz or VDAG or some of the others that are out there, you know, as far as as a teaching instrument, as us as kind of being the students, that would be a tremendous value if you were to take it. If you were to add one thing, that visual component would be a tremendous value. And then as things develop with Substrate and Archain and Polkadot, there may be this a pathway for it, and if we kind of see that, then reach out to Hashgraph and see what they're at. So just kind of speculating at this point, but there's certainly promise in possibilities. But the graphic component would be interesting to see.
Yeah, that's a really good point.
Cool.
So the you know about the Hedero Hashgraph network?
That
They're
one,
just the company, right?
Yeah, this is the Hedera.com.
Hedera.
And they have, well, it's a trust network, but where is it? They have Solidity, they're running Solidity contracts. So I believe they are doing validation. But it could be,
Strange. Yeah, I mean, I guess you can have pretty much any state transition function working inside of it. Even the EVM, I guess.
All right.
Yeah, for me, like the most exciting applications of Hashgraph, it seems like a technology that works best at small scales. Like it's really efficient, it's really fast. But you're running these like giant traversals through these big DAGs that are getting created, and depending on like how quickly events are being gossiped, like if you're gossiping like multiple times a second, then this hash graph is just going to explode in size. And so I think it's mainly best at like the really small scales. That's what I'd be excited in seeing it used for. Is like you could imagine some kind of swarm technology. You could even have like consensus on drones or something like that.
That's interesting. Is understanding the features and characteristics of Hashgraph. Okay, given that, what would be a real world application? And knowing that it's got to be in this small confined environment because of the bloat that it create. So that kind of helps think about, okay, that what are these possible use cases?
Yeah, and
the question becomes, how can you decentralize it?
Well, yeah, that'd certainly be the ultimate.
Yeah. I mean, a decentralized half graph running Joxy contracts, I think, would be really cool.
What kind of contracts?
Joxy.
Joxy. That's a new one for me.
That's Joshy's Roland.
Like it.
Or no, that's Roxy. I'm sorry.
Yeah, right. Okay, but I like your terminology. We'll have to share that with Joshy. The Joshy's Roxy.
Yeah.
This is great. Hey Jim, I had a couple questions regarding the calendar.
Yeah, you're a manager, right?
I'm possibly. So this session was Casper or Consensus. Did that start at? So we're in Eastern time zone. On the calendar, it had 8 a.m. But does Did it actually start when you hit record? Should it be 10 a.m.? So it has on there 9 a.m.
Yeah, well,
Oh, is
I
it
don't know if
still
you noticed,
saying
but
9?
in the channel, Joshi asked if we'd start at 9.
Oh, did you guys start it at 9 Eastern time?
Kayvon and myself came then.
Okay.
Gary, who said he was going to be there, and
I forgot.
and Josh himself did the show.
Okay. Yeah. Okay. I like it. Now, the other question is, there's a computational calculi collab. I haven't attended any of those, and I've been meaning to watch the videos. So, do you typically, after the Casper, do you move into the computational calculi? Do you?
Yeah. Well, you sort of attended one. I mean, the K framework session that I did last week, that was basically what we do in the computational calculi. That's at least one example of
Okay.
a discussion that goes on there.
Because
I
just
usually stop the recording and start another recording.
Yeah, right.
Gotcha.
Yeah.
Okay.
But
Well,
it's continuous.
gotcha. Now, in regards to computational calculi, since we're kind of moving in that hour, there's 12 sessions, 12 videos of computational calculi on YouTube of Greg presenting computational
right.
calculi, and
Yeah.
it was rich. The new guy from England who brought it to my attention. So I've watched the first 3, and to get a foundation for Rolang, that's helping me tremendously. And I think maybe Gary may even be aware of those videos. But my goal is to watch all 12 of those presentations, and then I think I'll be better oriented on Rolang. So just to share that with anyone who's interested.
Yeah, those are great videos. One of go ahead, Jim.
No, some people here attended them, right?
Yeah. So it's there's an audience certainly on the videos. He's teaching to a group.
Yeah, Tomislav was a part of most, if not all of them, and he recently presented a fixed up version of some like natural number